This video today is going to be the first lesson in momentum and impulse. When we talk about momentum, we also talk a lot about collisions, so that'll be part of our unit as well. But today we're focusing mainly on momentum and impulse. When you think about the definition of momentum, what do you think about when you think of momentum? Because sometimes what we think of in kind of a colloquial way matches up with the definition in physics, and sometimes it doesn't. So when we think of momentum, one thing that does match up with physics is how difficult something is to stop. That is a definition of momentum, and that works with the physics definition as well. Another thing about momentum is maybe we should talk a little bit about the formulas for momentum. One of the formulas for momentum is here, and oddly we use a P for momentum. M, of course, is always mass, and V is velocity. Now, the P is a little bit unexpected, but I think in physics we're kind of running out of M's, so we are going with P for momentum. So some way that you can remember that maybe is to think of a momentum. That's another way to think of momentum. Of course, momentum is the actual word, but why are we using P? I don't know. So P is for momentum. The units that we talk about with momentum is kilogram meters per second. And you can see that in the formula. Mass is kilograms, velocity is meters per second, so kilogram meters per second. Another way to say that is Newton seconds. And so if we think about it that way, we can see it's a little bit of force times time as well. Okay, let's think of some examples of momentum. Can you think of some things that have a lot of momentum and some things that don't have so much momentum? So again, keeping with that definition of how difficult something is to stop, something that has high momentum would be something that's very difficult to stop. Something that has low momentum would be something that's easy to stop. So think of some examples that you can consider of low momentum and high momentum. So I have some here, and I'm going to kind of go through one by one. High momentum, a golf ball. Low momentum, a ping pong ball. Because a golf ball has more mass to it than a ping pong ball does. High momentum, a boulder, again, has a lot of mass. Low momentum, a bag of leaves. That was in the crash course video. A high momentum, a high-speed train. That would be very difficult to stop. However, a slow-moving train, you maybe could stop that because the velocity is not so high, so therefore it's much easier to stop. And then an example from your own life, have you ever driven in your car when it's just you and put on the brakes and you're kind of used to how much pressure you have to apply to the brakes to stop the car? But then if you have all of your friends in the car and suddenly there's 4 or 5 people in the car, it's a little bit harder to stop. And you put on the brakes and you expect the car to stop, but it doesn't stop the way you think it's going to. The reason is it has more mass. It has the same speed, but has more mass. And all of that mass is making it more difficult to stop. It has more momentum. Okay, so when we talk about momentum in physics, of course, we can assign a numerical value to it. If we know how much mass there is and how much velocity there is, then we can get a numerical value and we can come up with our total momentum. An asteroid mass with 10 to the 6 kilograms mass moving at a speed of 50 meters per second, we would take 50 times 10 to the 6th, or in other words, we could move that decimal over one place and say 5 times 10 to the 7th. And once again, our units is Newton seconds, or you could call it kilogram meters per second. But in this case, we have 5 times 10 to the 7 Newton seconds. A high-speed train with a mass of 180,000 kilograms and a velocity of 3,000 kilometers per hour. Okay, if we're talking about SI units, we need to change some things here. One thing is we need to take 300 kilometers per hour and change that to meters per second. Now, kilograms is fine the way it is. So over to the left here, we can convert 300 kilometers per hour over to meters per second using our unit analysis. And so we're going to take a second with our calculator and see what that comes up to. So I'm getting 83.3 repeating meters per second. And if I, again, take my calculator and multiply those together, I get 1.5 times 10 to the 7th. And once again, your units can be kilogram meters per second, or they can be Newton seconds, either one. A linebacker, 120 kilogram linebacker with a velocity of 10 meters per second. Okay, so we take 120 times 10. I'm going to leave that in scientific notation just because everything else is in scientific notation. And then lastly, a proton with this mass and this velocity. Okay, we haven't talked about scientific notation a lot in this class, but the way you multiply these is you would multiply your 6 times your 2, and that gives you a 12. And then you take negative 27 plus 8, and negative 27 plus 8 is a negative 19. But of course, for scientific notation, we want it to be 1.2 times 10 to the negative. And since we moved it back a decimal place, we have to change our exponent. So that's going to be negative 18 kilogram meters per second. Okay, so that's the calculations of them. And so now we're able to look at which one has the most momentum, which one has the least momentum. So obviously the proton has the very least momentum. We can label that number 4 because it's the 4th one. Our highest momentum is going to be the asteroid. The second highest is the high-speed train. And lastly, or third, I guess, is the linebacker. And in each of these cases, we had a certain mass that plays into it and a certain velocity that plays into it. So like just to compare the first two, the asteroid has a much larger mass, but the velocity is not as high. So all of these examples have two things going on here. We've got a certain amount of mass involved, but we also have a certain amount of speed involved. And so each of these has a certain amount of momentum based upon how much mass there is and how much speed there is. Just for instance, if you look at the speed of the proton, it's got a very large speed. However, its mass is so small that it's interacting with that. So you have to consider both, the mass and the speed. Okay, and then another thing is momentum or momentum is a vector quantity. Unlike energy. So when we talk about energy, energy does not have a direction to it, but momentum does have a direction to it. If you've got a car going to the right, its momentum is going to the right. And so the vectors are important here with momentum. But in energy, the amount of energy something has is not a vector, it is scalar. Another concept is impulse. And this is interesting because this is, again, one of those things where the colloquial words may not match up with the physics words. So let's just kind of take a look at this and learn a little bit about impulse. While knowing how much momentum or momentum an object has is nice, we are usually interested because we are looking to change the object's motion. A change in momentum is known as impulse. So back to the car. You have this car, and it is driving with a certain amount of velocity, and so it has momentum going that way. Typically, we want to change that somehow, like maybe we want to stop the car, or maybe we want to speed up the car. And so that's where impulse comes in. And when something is moving and then it stops, there's a certain amount of impulse that's going to happen. And how rapidly it stops is going to be a certain amount of impulse, whereas something that maybe can cushion it a little bit more is going to be less impulse. So for instance, let's talk a little bit about Newton's second law. When we think of Newton's second law, we think of F equals ma. But actually, that's not how Newton originally thought of it. Let's go back to what I was talking about a minute ago with the equation. We have momentum equals mass times velocity. And then we came down here and we looked at the units and we said kilogram meters per second because that's mass times velocity. And then we said or Newton seconds, and notice that that is force times time. And so another way to talk about momentum, another related equation is going to be force times time. And so another way to talk about momentum, actually we're going to talk this time about change in momentum. And change in momentum is force times time, or force times change in time. And we use, for impulse, we use the capital letter I. Some textbooks use a capital letter J. Why do they use a J instead of an I? I could not tell you. It's just another one of those things where we only have so many variables, and so we're having to move some stuff around. Okay, but this formula is another formula for momentum or impulse. Change in momentum is impulse, and it has this element of time involved in it. And so if we take a second to rearrange this formula, like if we divided by delta t on both sides, then we would get that force is change in momentum over change in time. And by change in momentum, we mean the final velocity minus the initial velocity, the mv final minus the mv initial. Mv is our momentum. And so now we can also pull out and factor out our m, because it's the same object, the same mass that's moving the whole time. And so if we factor out our m, we get m times v final minus v initial, still over change in time. And so I can rearrange that, how I write it, and I can say mass times change in velocity over change in time. Well, what's change in velocity over change in time? It's acceleration. And so we get now back to F equals ma, which is what we know of as force. But you have to understand that going back to Newton's second law, it actually starts off by saying the change in momentum over change in time is the definition of force. Okay, let's look at an example. Common sense is that when you're jumping off of things, it's a good idea to bend your legs. Why? So think about jumping off of, I don't know, stairs or a wall or something, whatever you're going to jump off of. Why do you want to bend your legs? Well, obviously you kind of want to cushion that fall. And this also goes back to, some of you might have done an egg drop experiment in science classes, where you try to drop an egg and see which one, doesn't break. Well, both of those concepts, whether you're dropping an egg or whether you're jumping off something, you want to cushion that fall. Well, why does cushioning the fall help? Well, the reason, as far as we are concerned, is it increases the time. And if you're increasing the time, that means you're going to lessen the amount of force, because look at our equation. Okay, so let's say you jump from a 1.5 meter ledge. How fast are you going when you land? Well, we're going to have to do a little bit of kinematic review to get back to that. So let's go back to this kinematic equation. And final velocity is what we're looking for. Initial velocity, we are assuming that's 0. Like you just kind of jump off you just kind of barely jump off the ledge. You're not like taking a huge leap. Your initial velocity is 0. So let's assume that's 0. So now we have 2 times acceleration. Well, acceleration is 9.8 meters per second squared. And our delta x is given to us as 1.5 meters. And so now we can just calculate that. And so I get 29.4 meters squared per second squared. If I take the square root of both sides, I get 5.42 meters per second. So I am going 5.42 meters per second. Okay, if you bend your knees while landing, it will take you approximately 0.3 seconds for you to come to rest. How much force does this require? Well, let's go back to this force equation that we had up here. Force is the change in momentum over the change in time. Change in momentum means mv final minus mv initial. And then change in time is given to us as 0.3 seconds. And we said we could factor out that m. And our v final minus v initial, our v initial was 0, so our v final minus v initial is 5.42. And we're going to divide that by 0.3. So let's just take 5.4 divided by 0.3, and we basically get 18 times the mass. And the force is measured in newtons. So if you bend your knees, then you're going to experience 18 times the mass of newtons. Okay, what about if you don't bend your knees. If you don't bend your knees, it's going to take 0.005 seconds for you to come to rest, much quicker. And so this time, our momentum is the same. Our final minus initial is still 5.42 m. But this time, instead of dividing by 0.3, we're going to divide by 0.005. And when we divide that, we get 1,080 times m newtons. So if we have 1,080 times m, that is 60 times as much force that you're experiencing in your knees. And so that's going to obviously affect your whole body a lot differently. One thing is if you are going to study any kind of medical related fields, a lot of physics goes into things like physical therapy and a lot of different areas of medicine, but you can imagine kind of the sports medicine aspect of this, of how much force can your knees take before your knees get injured. So this is something to consider. In any case, if you are bending your knees, you are lessening how much force you have by a factor of 60. It is 60 times less force if you bend your knees compared to if you don't bend your knees. That's a huge deal. That is impulse. Impulse is related to how much time is going on. And the time is going to be what's going to be affecting the force and the magnitude of what's happening. Okay, one thing when we do video notes is if there are things that we have discussed that you're not sure about, that you will still want to come back to class tomorrow and ask some questions about, please write those questions down in the margin. Somewhere in the margin here, write down the questions that you want to ask from this page.